work. In the present work, a facile selective beta-allylation of indole has been accomplished employing baylis-hillman bromide as allele source under visible light photoradar catalysis in the presence of lithium biphenotyl complex and new entities. Indoles are motifs of great synthetic interest due to their presence in many natural products and biological important molecule. Consequently, numerous efforts have been made towards the development of new methods for the selective functionalization of indole at RC2, RC3 position. In this perspective, a number of significant reports have appeared, including C3 allylation of indoles using baylis-hillman acetate in the presence of indium bromide. However, the use of baylis-hillman bromide for the C3 allylation of indoles under visual light catalysis is not yet explored. In the present work, we have taken indoles and baylis-hillman bromide with ruthenium bipyridyl complex and potassium hydrogen phosphate as a base, stirred at room temperature to find C3 allylated indoles. In this reaction, baylis-hillman bromide as allele source has been used as allele source under visible light photoradar catalysis. Regioselective beta-allylation of indoles has been accomplished, and it's required very low catalytic loading. The reaction was optimized in various reaction conditions. First of all, using Y and potassium hydrogen and phosphate was taken in istonitrile and stir for the 10 hours, and low yield of the product was obtained. Next, we move to another photocatalyst rose bengal with potassium hydrogen phosphate in istonitrile solvent with in istonitrile solvent, and further the decrease in yield was achieved. Next, we move to ruthenium bipyridyl complex and potassium hydrogen phosphate base, and a good yield of the product was obtained. And next we optimize the amount of the photocatalyst, and the 1 mole % of photocatalyst was optimum for the present conversion. Next, we move towards the scope and applicability of the present reactions. Various baylis-hillman bromide were synthesized, and it was allowed to react with various substituted indoles, and formation of product was achieved. All the products are shown in the table, and in which we seen that the baylis-hillman bromide methyl acrylate derived baylis-hillman bromide form the E-selective product with indoles, while in the case of acrylonitrile derived baylis-hillman bromide give Z-selective products in high to good yield. This is the RP diagram of one of the product of acrylonitrile derived baylis-hillman bromide, which allylated to indoles. This is the mechanism of the reaction in which baylis-hillman bromide undergoes single transfer with the ruthenium bipyridyl complex in the excited state, and addition with light undergoes debromination and form the allyl radical. This allyl radical combined with indole radical cation, which is generated from the single electron transfer with the oxidized ruthenium complex, and these two intermediate combine to form this intermediate A, and which aromatized to form allylated C3 allylated indoles. This is the general procedure. A mixture of indole 1 millimoles and equivalent amount of baylis-hillman bromide with potassium hydrogen phosphate in 1.5 equivalent reactor in presence of photochromonium bipyrrole complex photocatalyst as photocatalyst in 1 mole percent amount in acetonitrile in 3 ml placed in closed glass vessel were irradiated with Lagan reveal blue LEDs from the bottom side at room temperature for 10 hours. After the completion of reaction, the mixture was quenched with water and then extracted with ethyl acetate. The combined organic phase was dried over in hydrous sodium sulfate and concentrated under reduced pressure to yield the crude product, which was purified by gazel chromatography using 10% ethyl acetate hexane mixture to give the pure product. The product was identified by the confirmed by the 1S NMR spectra and 13C NMR spectra, NOGI's NMR spectra, NOGI and HRMS and SRD data. Conclusion. In conclusion, a simple and radioselective C3-allylation of indoles using baylis-hillman bromide has been explored under visible light photoredox catalysis at room temperature. The methodology is endowed with broad substrate scope and good functional group tolerance. The product is accessible to find various carbocyclic and heterocyclic products. We thank to CSIR New Delhi and SCRB New Delhi for the financial support, novelty and advantage. The present development of new methodology for the synthesis of potentially bioactive molecule implying natural resource like visible light, and designing a protocol to access atom economy, mild and efficient pathway, minimization of formation of side product and waste product in the reaction, implementation of BH bromide as a new substrate under the visible light photoredox catalysis, optimization, isolation, characterization of synthesized compound. All the starting materials are easily available, and it uses renewable resources. Very low catalytic loading is required, and selective formation of product occurs. Thanks to all of you.